All right, so the first order of business, let me just kind of start over here. So in Blackboard, I made an update in this area, important course info, orientation, and it's the page for on-campus proctored exams, which you can click the link, which takes you to it. And the change that I made, well, not really change, I should say update, or newly added stuff, is kind of in the middle, maybe towards a little closer to the bottom here, but there is an update on this page. It says, please make a note that exams 2 and 3, okay, so the one that's on Wednesday and then the exam after that, is going to be proctored in a different location, and the location for these 2 exams, and it's only going to be these 2 exams unless something comes up. But exams 2 and 3 are going to be administered in the liberal arts building, specifically room 200. And the liberal arts building is on the south end of campus. It's right behind the McDowell Student Center, which is where our testing center is at, as well as some of our general offices like financial aid, admissions, and so on and so forth. I like to call it the glass building. Directly behind that is the liberal arts building, which is where exams 2 and 3 are going to be proctored. And room 200 is one of the middle hallways. I believe liberal arts has 4 hallways. The best way for me to describe where room 200 is at is that it's right next to our auditorium. So we do have theater classes, and they do put on live productions. And where they do it at is in this building, liberal arts. So in the very center of the building is an auditorium. Our room is going to be right next to it. All right, so like last time, I'll be standing outside the door to kind of help corral you into the room where we'll take our exam. Okay, the best place to park, by the way, south parking lot, or if you can find a parking spot in front of the McDowell Center, um, that works too. But just want to make it crystal clear that we're going to be in the liberal arts building for exams 2 and 3, and exam 4 will be back in the forum building. Okay, so any questions about that? Now, all of the procedures for coming onto campus are the same as last time. For instance, with the coming to campus procedure, you can click on here. And just like last time, you will have to fill out a health self-report. Okay, so the same form that you used last time. You fill it out the day of the exam, not any sooner. And once you get your green check mark, you're allowed to fully enter into the liberal arts building, in which case you can find your way to room 200. Now, I believe, and I will confirm this, I believe the entrance for students is on the very south end of the building, so adjacent to the parking lot. All right, so I'll double check on that, and if it's different from this side of the building, then I'll include it in the announcement. Otherwise, if you don't see anything about student entrance, you can assume that it's on this side of the building. All right. As for the exam itself, the exam will be similar in format to this practice exam. Right, I felt maybe it might be to our benefit to review maybe with a practice exam. So we'll do that once we take our break. And by the way, there is a practice exam link in my math lab, in which case, you have any number of attempts on the practice exam in my math lab, of course, and I will be offering a bonus opportunity for that. Very similar to the bonus opportunity from exam one, where if you meet a certain score on any of your attempts on the practice exam, so if you meet a certain criterion, I'll insert some bonus points for you in the grade center. But the exam will be similar in format to what we have here. Okay, um, and as we work our way through this, we're going to see that there's some multiple choice and some response and so on and so forth. But we will be taking the exam at 9 o'clock on Wednesday, and then there's going to be a 1 hour time limit. And once time is up, um, you know, we won't be meeting for class virtually or physically. We'll just kind of do the same thing as last time, where I'll have an upload of video lessons for the section that we would normally do if we were meeting in person after the exam. Okay, so do you have any questions about anything I just went over? All right, well, if not, then let's go ahead and take a 5-minute break, or maybe a 6-minute break. We'll start at 10, all right? We'll go through this practice exam too, okay? So I'll see you at 10. All right, gang, you ready? Here we go. Start with number one. Want to determine whether the relation represents a function. So this is a mapping diagram. Our inputs would be the names Alice, Brad, and Carl. The outputs would be snake, cat, and dog. And I want to focus on Carl in this mapping diagram. Carl is being assigned two different animals, two different outputs, cat and dog. Now, since Carl is getting two different outputs, this would not be a function. All right, so you can think of Alice, Brad, and Carl as x values and the animals as y values, in which case there's one x value in the mix that's getting two different y values. So remember, for a function, inputs can only be assigned one and only one output. So the fact that Carl gets two different outputs would mean that this is actually not a function. So your answer to this would be part C, or option C. For number two, we have a set of ordered pairs. And what you want to be looking at in the set of ordered pairs to determine whether or not it's a function are the x values, which are -2, -1, 0, 1, and 3. Now, if any of these x values are repeats, then this would not be a function. But looking at our x values, do any of them repeat each other? Nope, there are no repeats in x values. So this would be a function. Okay, so our choices are between A and B. And to determine which of those two options it really is, note that the x values represent the domain. And if we write out the domain by hand, the domain would be -2, -1, 0, 1, and 3. We could look at the range as well, but options A and B have differing domains and ranges. If our domain consists of these 5 numbers, we'd want to go with option B because it has a matching domain. All right, so number 2 would be option B. This right here is more or less a written response type question. They call it short answer. But with this graph, we want to provide a variety of things. We have to first determine whether the graph is that of a function. And we could quickly just do that mentally. The vertical line test is something that this graph would pass. Any vertical line going through our graph would only cross the graph in one spot. So it's definitely a function. And it says if it is a function, use the graph to find its domain and range. I'm going to add something to this graph, and that's going to be arrowheads on the ends. Now, to figure out the domain, first of all, note that this graph is fully connected. So between the ends, we would include all the x values. But there's also an indication that this graph, as you extend it, further and further, not only is this part of the graph going downward, but it's also, scooching over to the left. And so is the other end. Well, it's going down, and as it goes down, it scooches over to the right. So I like to say that, this graph does essentially just keep on widening and widening as you go further down on it. And in order for that to happen, you would need to use all of the x values from the x-axis. Okay, so this graph, widens out, so much so that, you begin using x values that are down at negative infinity as well as positive infinity, i.e., all of the x values from the x-axis are going to have to be used in order for that to happen. So the domain would be all real numbers. Is the range all real numbers? Let me ask you this. Is there a largest y value on the graph? Yep, largest y value is 4. And all of the y values that are less than 4 are involved as y coordinates of our graph. And all those y values are heading down to negative infinity. Now we can include the 4 since that point, which appears to be at negative 1 comma 4, is not an open circle. Okay, so 4 is being used as the y coordinate there. But keep in mind with the range or the domain, either of those, when we write interval notation, we always start with the smaller number first. And in the case of the range, the smaller of those numbers would be negative infinity. So negative infinity parentheses, and then the larger number on the range here is 4, and we can include that. It also wants us to find intercepts, and there are two types, x-intercepts and a y-intercept. And then it wants us to make a comment about symmetry. Let me get rid of some of my shading here. I'll get rid of this point as well. I don't want it to distract us. Let's talk about the x-intercepts. It appears as though we have a positive x-intercept at 1, 0, and a negative x-intercept at negative 3, 0. So let's write those down as the x-intercepts. And then, does this graph have a y-intercept? If so, where's the y-intercept at? 0, 3. Yep, you got it. Now, since this is the graph of a function, the only possible type of symmetry it could have is y-axis symmetry or origin symmetry. Let's take a look at the y-axis. Do you think that this graph is, for lack of a better expression, evenly distributed on both sides of the y-axis? You know, for example, you know, is there like a mirror image of what's to the left of the y-axis to what's on the right of it? No, not at all. And you know what? You can actually argue this from a numerical standpoint looking at the intercepts. If this graph had y-axis symmetry, then the x-coordinates would be opposites of each other, you know, when the y-coordinates are the same. But here we have the same y-coordinates, 0 and 0, and the x-coordinates are not opposites of each other. So there's no y-axis symmetry. Do you think there's origin symmetry? There wouldn't be any origin symmetry either. Yeah, and if we wanted to, you know, we could try to approximate a point, you know, in quadrant 3 and see if it corresponds to anything in quadrant 1 or quadrant 2 and quadrant 4, or even do reflecting, you know, reflect across the y-axis and then the x-axis. And what you would find is that your end graph doesn't match the original. So unfortunately, this graph doesn't have any symmetry whatsoever. So I'll put none. All right, any questions about that? If not, then let me kick off number 4 to you. This is a multiple choice question. I just want you to evaluate the function with the expression x plus 1. All right, give you a minute or so to do that. Be sure to FOIL, if you plug this into your function and there's a power on it. All right, so I'll check in with you in about a minute or so. All right, so f of x plus 1, what we're going to have to do is take the expression x plus 1 and plug it into both of the x's that are part of the function's expression. So instead of just simply x squared, it should be x plus 1 quantity squared now, minus 2, all over quantity x plus 1, minus 5 on the bottom. I mentioned FOIL because in the numerator, we have x plus 1 quantity squared. So that will require FOIL. And what I mean by that is write out 2 copies of x plus 1, FOIL them out. You don't need to do any foiling on the bottom, nor any distributing. There's nothing in front of the parentheses. So I'm going to release that from parentheses. And we'll go ahead and get to the FOIL part. When you FOIL out x plus 1, you're going to get x squared plus 2x plus 1. And then don't forget the minus 2. Then on bottom, you can combine 1 and negative 5 together to get x minus 4. Now there are some terms you can combine in the numerator as well. We can combine positive 1 and negative 2. And our final answer should be x squared plus 2x minus 1 on top and x minus 4 on bottom. And that would be option D. Did you guys get option D when you worked this one out? Sweet. All right. Let's keep the gravy train rolling. For number 5, 6, and 7, we're going to find the domain of functions that are presented to us as equations. Now, having gone through section 4.1 already, we can kind of cheat a little bit for number 5. This right here is an expression for a linear function. And what did we learn about the domain of linear functions? The domain for a linear function is always all real numbers. And if we take a look at negative 2x plus 3, there's no division by 0 possible. And there's also no square roots of negatives possible. So these two taken at the same time would lead way to a domain of all real numbers, which if you look, that's there's a typo. The answer should be D. Let's cross that out and put negative infinity to positive infinity. So I'll be sure to look out for any typos like that before printing the exams for you guys. But the domain should be negative infinity to positive infinity. Now, if we look at 6, there is a possibility that we could divide by 0 because we have x in the denominator. And you may recall that what we do is we hunt down the values of x that make the denominator 0, and then we throw them out of the domain. Now, x squared minus 9 is quadratic, but it's a special type of quadratic. It's one that's a difference of 2 squares because 49 is the same as 7 squared, right? So what you want to do is factor this as x minus 7 times x plus 7. And then we know by now to set each factor equal to 0 to solve for x. And one value of x is 7. Another value of x is negative 7. Now, in terms of domain, these are two values of x that we don't want to get plugged into our function. So in the context of domain, we actually don't want x to be 7, and we don't want x to be negative 7, because they create division by 0. So what we're going to do is draft up a number line. We'll put these two values on it. And it's just these two values and only these two values that we cannot use, which means that we can use anything to the left of negative 7. Okay, that part goes all the way down to negative infinity. Parentheses. We can use the stuff between the 7s. And we can also use the stuff to the right of positive 7. So what answer choice would correspond to the number line that we have here? You got it, option C. Yep. For number 7, we have x over the square root of x minus 7. So we got to be privy to a couple of things here. Okay, first of all, there would be a value of x that creates division by 0. Can anybody tell me what value of x would create division by 0? So 7 would create division by 0, so we don't want x to be 7. We also don't want the expression x minus 7 itself to be negative because it's inside a square root. So in order to satisfy both things at the same time, x cannot be 7 and x minus 7 cannot be negative. The way to work with the domain here is to form an inequality using x minus 7. And we'll say that, well, in order for everything to work out in terms of plugging values in, the only restriction we would need is for x minus 7 to be greater than 0. Okay, and the reason for that is because x minus 7 is inside of the square root. Now, when we were doing a problem involving a square root, we had the bar underneath the inequality symbol. But the reason why I'm leaving off the bar is because we should not be including the number 7 itself because of where the square root is at. Square root's in the denominator. So we're going to solve this inequality simply by adding 7 over to the right-hand side. And that tells us the conditions on x. Our x values have to be greater than 7. And if we draft up a number line, that would be x values to the right of 7. And again, we're not going to include 7 this time because 7 would create division by 0. So we would be looking at option A. Make sense? All right, let's move on to problem 8. This is an application problem involving functions, specifically a combination of functions in a special way. It says here, a firm is considering a new product. The accounting department estimates that the total cost, given by C of X, of producing X units will be given by C of X equals 90X plus 4390. The sales department estimates that the revenue R of X from selling X units will be 100X. But it says that no more than 851 units can be sold at that price. It says find and interpret R minus C of 851. I'm going to break this up into a couple of parts. I'm going to neglect 851 for a second, for this part one. And I want to take a look at what R minus C of X would be. Now, R minus C in parentheses, this is something we addressed for section 1. This is really asking you to subtract the two functions. So a better way of looking at this is as R of X minus C of X. Which, by the way, I'll do a little recall statement over to the right. R of X minus C of X gives profit, P of X, right? Because if you take the amount of money brought in, which is revenue, and you subtract off the cost, then any money that's left over is money you get to keep in your pocket. That's the profit. So R minus C of 851 is referring to profit, which if you look at the answer choices, they're mixing in that word profit. Now, before we take a peek at the X value of 851, I'm going to replace R of X with 100X, and then we're going to subtract the cost function, which you'll want to use brackets or parentheses, some sort of grouping symbols, because you're really subtracting two terms, both 90X and 4390. The grouping symbols remind you that you need to distribute the minus sign to get 100X minus 90X minus 4390. All right, and that's going to simplify to 10X minus 4390. Now, the reason why I did that is to help us clinch what R minus C of 851 is going to equal. We basically take 851 and we plug it into our profit function, which that's what 10X minus 4390 represents. That's our profit function. I'll make a note, P of X equals 10X minus 4390. And we're going to take 851 and simply plug it in for X. And does anybody want to punch that into your calculator and let me know what you get for the profit? Confirmation on 4120? I'll actually confirm that. I did get 4120 as well. Let's take a peek at these answer choices. There are really two options that involve 4120. Option A, however, notice that they have a negative in front of it, and option C. Option C says 4120 profit, meaning that the income exceeds costs. It is worth it to develop the product. I'm not really sure why, including that it's worth to develop the product is included. But I think we have enough information based on the second step of this problem to confirm that C is going to be our answer choice. Because if you look at the other options, B and D, they have different values for profit. You can do a little elimination there and deduce that option C would be our answer. Any questions about that? Let's move on to 9, where we will review the difference quotient. Okay, the difference quotient is given by this formula right here, which if you get a difference quotient problem, the formula will be provided for you. Okay, so no need to memorize that, although, if you want to, not a bad idea. And we're going to adapt the difference quotient formula to our expression 4x squared. And I'm going to break this up into 3 parts. The first part is going to be to figure out what the expression f of x plus h is. Now remember earlier we plugged x minus 1 into a function, and the way we did that was by taking the expression x minus 1. In this case, it's going to be x plus h. And we take that expression and we plug it into all the x's, which in our function there's just one x. So we're going to rewrite 4x squared as 4 times quantity, x plus h squared. And what do you think we might want to do from here? How about FOIL? Okay, so we'll FOIL. And the way I'm going to do this is by opening up some brackets so that I can include 2 copies of x plus h. Okay, go ahead and take a moment to FOIL out the x plus h's, and we'll figure out what to do next. All right, after foiling and simplifying, that should be x squared plus 2xh plus h squared. And one more thing to do for this part, and that's to distribute 4 to all 3 terms. When you do so, you're going to get 4x squared plus 8xh plus 4h squared. And that takes us to part 2, where we're going to subtract the original version of the function from what we just got in part 1. So we're going to take 4x squared plus 8xh plus 4h squared, and we will subtract 4x squared. Now it's totally not necessary to write it out this way, but I will. And what I mean is you don't need the brackets around 4x squared, but it's a good idea to get in the habit of including brackets, because a lot of times the original function has more than just one term. And so using brackets would clue you in as to needing to distribute the minus sign to all the terms. In this case, it's just going to be 1, and that's 4x squared. And when you do that, you actually get some canceling between 4x squared and minus 4x squared. And this is what's left over when those cancel, which takes us to step 3, where we divide that expression by h. And based on how a couple of the answer choices are formatted, I think what we might want to do here is maybe consider factoring out a GCF in the numerator. Can anybody type in what the GCF in the numerator would be? Well, between 8 and 4, you can factor out a 4. And it looks like each term has a copy of h, at least one copy of h, so I'm going to take that out. And you'd be left over with 8x plus 4h. And on the bottom, we still have h. And what's nice about factoring the GCF out is that we get some canceling. So the 4 will remain, and so will the factor of 8x plus 4h. Oh, I gaffed a little. That should be 2x plus 4h. And I'm not sure what happened there. A little slip. All right, so when you factor out 4h, you should get 2x plus h. And let me fix it down here. The h's still cancel. 4 is left over in front of the parentheses, and 2x plus h will remain inside the parentheses. So this should actually be our difference quotient. Not sure what happened in the previous step. A brain fart. But as you can see, our answer to this one should be option D. Okay, they have the 4 factored out, and inside the parentheses is 2x plus h, which is exactly what we got. So option D. D for difference quotient. All right. Move on to problem 10. They want us to decide whether the function is even, odd, or neither. Let's first test to see if the function is even. And when you're provided the graph of a function instead of the equation for it, you have to do some reflecting. Okay, a function is going to be even if it has y-axis symmetry, and a function is going to be odd if it has origin symmetry. I'm going to draw a coordinate plane for our y-axis symmetry. And what we do is we can do this in pieces. We can take the piece that's in quadrant 1 from our original function and mirror it across the y-axis. And when you do so, it ends up looking like that. And we can also take the part of the graph that's in quadrant 3 and mirror that across into quadrant 4 to get our completed y-axis reflected graph. Now, it's not 100% accurate or drawn to scale, but if it were, would this line up with the original version of f of x? No. So it's not even based on that. So since it's not even, we're going to proceed to do an x-axis reflection using our most recent graph. And what that means is, let's maybe start with the part that's in quadrant 2. We're going to mirror that across the x-axis. Give us a piece looking like that. And then we'll take the piece that's in quadrant 4, mirror it across the x-axis to get the rest of the graph. Now, all things considered, after doing our x-axis reflection to the y-axis reflected graph, does it match the original version of the graph? Yep. So after doing both the y-axis and x-axis reflection, we can conclude that the graph has origin symmetry, which would mean it's what kind of function? Odd. You got it. So it'd be answer choice B. Okay, any questions so far? Alrighty, let's move on to 11. Same kind of question, but different setting. We have a function presented to us as an equation, 6x cubed minus 9. Now, when we were doing this back in the notes, it would be for section 3.3, by the way, we were making kind of like a little chart. In one column of our chart or table, we put the original version of f of x. The next column of the chart, we worked out f of negative x. And then the last column of our chart, we took the opposite of the original function. So let's fill this out. The original version of our function is 6x cubed minus 9. F of negative x requires that we plug negative x in for regular x. So 6 times negative x cubed minus 9. And then for the very last column, we distribute a negative 1 to our original version of the function. Now I'd like you folks to take a moment to simplify the expressions that we have in columns 2 and 3. And we'll go over it and determine whether we have an even, odd, or neither function. So I'll give you a few moments to take care of the simplification in columns 2 and 3. All right, for column 2, when you raise a negative to an odd power, it remains negative. So for that reason, I'm going to rewrite this first term as minus 6x cubed and bring down the minus 9. And then, of course, we'll distribute negative 1 to clear parentheses with our last column to get negative 6x cubed plus 9. Do any of our resulting expressions match within the table? We have some close calls, don't we? Well, we have one close call, uh, namely with the second and third column. They both start with minus 6x cubed. However, what's happening with 9 is different. Okay, any difference, regardless of how big or small it is, between the expressions would imply that they're not equal to each other. And of course, these two don't equal the original version of the function. So what's our answer here? So no matches. Makes me want to say no manchas. No matches, which would mean that we have a neither function. So option C. All right, let's move on to 12. So using a graphing utility, use a graphing utility to graph the function and approximate any local maxima or minimum. So we'll see if the graph has any high or low points, and if it does, we'll use the graphing calculator to identify them. And once we identify them, it gives us a way of figuring out where the function is increasing, decreasing, or constant. All right, and of course, if we have to do some rounding, we'll round to 2 decimal places. So here's our function, and what we're going to want to do is enter it into y1. And we'll sketch out the graph once it's produced for us. Let me go to my graphing calculator. Go to y equals small minus sign, negative 0.3 x cubed plus 0.2 x squared, so on and so forth. Do zoom 6. Okay, you guys getting a similar graph? Okay, so we definitely have a maximum and a minimum. Looks like we have a maximum in quadrant 1 right here. That would be a local maximum because there are points that are higher than it. And then it looks like we have a local minimum in quadrant 3. And that's the local minimum because we have points that are lower than it on this right end of the graph. So let's start with the maximum that's in quadrant 1. In the calculator, you press second trace, and for maximum, you select option 4. And remember, you have to answer the 0 feature questions here, left bound, right bound, and guess. And since this is the point that we're interested in, a left bound would be on this side of the top of the hill, if you will. I'm going to scooch my cursor a little closer to the left-hand side of where the high point is at. Press enter. And then for a right bound, we want to go to the other side, so maybe somewhere right here in our graph. And then for your guess, just move your cursor to the top of the hill, press enter. And can I get confirmation on 2.34, 1.61? Great. All right, I'm going to give you a moment to find the minimum. Okay, so the minimum's down here, the very bottom of the valley in quadrant 3. Okay, second trace, but you'll want to use a different option. In this case, it'd be option 3 for the minimum. Okay, so I'll give you a moment to do that, and once you find it, if you could type it into the chat bar, that'd be helpful. All right, you guys still with me? Here we go. I'm going to sketch out our graph. real doohickey like that. Yeah, we figured out the local maximum. It was at 2.34, comma 1.61-ish. All right, thanks, Danielle. Yep, that is the coordinates of the local minimum, negative 1.90, comma negative 9.82. I'm going to go to 2 decimal places with the y-coordinate. No problem. All right, let's start fleshing this out. Say local max, that's at 2.34, comma 1.61. There's a spot for the local min. They also want us to see where the function is increasing and decreasing. To help us with that, I'll use red. We'll make tick marks on the x-axis corresponding to our extrema. Negative 1.90 will be for the tick mark on the left. That's the x-coordinate of our minimum. And then 2.34 for the x-coordinate of our maximum. And remember, to answer increasing and decreasing problems, you first have to determine which parts are doing what. And then based on sections that are increasing or decreasing, the official answers come from the x-axis. So the answers to increasing and decreasing problems are always based on sections of the x-axis. Now, if we start here on the graph with our finger, you'll notice that your finger slides down on the page, and that's because this is an area of the graph that's decreasing. And this part of the graph decreases until it reaches the bottom of the valley here. And once it goes past this local minimum, we get an area of the graph that's increasing. In other words, your finger would be sliding up on the page for this section of the graph. And then once we get past the local maximum, our finger would be sliding down on the page from there on out. So we have 2 sections where it's decreasing and 1 section where it's increasing. I'm going to start with increasing. Okay, this graph is increasing between the x values of negative 1.90 and 2.34. Now, so we don't confuse it with, an ordered pair, as you probably saw in my math lab. You can use brackets on these x coordinates, or you could use parentheses. I tend to gravitate towards parentheses, but I know for something like this, if I used parentheses, it might look like an ordered pair. So I'm going to leave it with brackets. And let's get decreasing. Okay, this graph is decreasing starting from negative infinity, leading up to negative 1.90. I guess I'll be consistent by putting a bracket on 1.90, and then it picks back up with 2.34 and continues on to positive infinity. And I think that's all we needed to do for problem 12. You guys have any questions about the solution? All right, so we're getting close to the end of our class session today. I would like to squeeze in number 14, and then I'll have the solutions uploaded to the remaining problems on Blackboard later today. So let's do 14. Which is related to a box problem, very similar to one from the notes for section 3.6. And it says here, a box with an open top is going to be constructed from a rectangular piece of cardboard with original dimensions of 14 inches by 27 inches. And they're forming this box in the same way, as we were doing in 3.6. They're removing x by x squares from each corner. And doing that will help you form four sides of a box that become sides once they're folded up. Want us to express the volume of the box as a function of x, and then find the value of x that gives the maximum volume. And then afterwards, what is the maximum value? All right. What I'd like to do is construct what's called the rectangular base of our box. And I'm going to insert the rectangle inside this diagram. The length and width of this orange rectangle will be the length and width of our open box. Keep in mind we're removing x by x squares from each corner. And in doing so, we shrink down the original dimensions of 27 and 14. So if that's making sense, can anybody give me an expression for the length of the rectangular base if it starts out as 27, but we subtract a pair of x's from it? It would be 27 minus 2x. So we can consider that as our expression for the length of the box. As for the width, okay, it starts out at 14, but we remove an x from one side and an x from the other side. So that becomes 14 minus 2x. Does anybody recall what the height of the box is dictated by? So remember, the height of the box is determined by the size of the square corner that you're removing. So the height of the box is going to be x. Now we need these three dimensions of our box because you'll recall that volume from geometry is length times width times height. You can use 27 minus 2x as your length, 14 minus 2x, as your width, and x as your height. So when you replace L, W, and H with these expressions, do use parentheses for a couple of them. And I will give you the FOILed out version of this function. Just in the interest of time, it would be 4x cubed minus 82x squared plus 378x. Now, in order to find the maximum volume and the value of x that creates the maximum volume, you would want to use your graphing calculator to graph this function and see if there's an absolute maximum. And I'm going to provide you the window settings that will work for this. And if you get a problem like this on the exam, I'll be sure to provide the window settings for you on there as well. That way you're not wasting any time guessing and checking with your window. I would recommend setting x min to 0 and x max to 7. X scale you can leave at 1. The y min I recommend using 0. And for y max, 600 is what I found to be a good y max. And then you can go by any units on the y-axis that you wish. I think what I did is I went by 50s. So let me just go ahead and mark the axes accordingly. So the furthest tick mark on the right will be 7. Furthest tick mark at the top of the y-axis will be 600. And what you end up getting when you graph this function is what I am now going to be calling a half Pringle. And you're interested in the highest point on this graph, which you can find using the maximum function on your graphing calculator. And after class, if you want to take a few moments to verify this, 2.94, comma 504.19 are going to be the coordinates of the absolute maximum. So, with regard to the question, the size of the square, oh, thanks, Daniela. The size of the square that should be removed for the maximum volume is approximately 2.94 inches, and the corresponding volume is approximately 504.19 inches cubed. All right, folks, we are just out of time. Do you have any final questions before I dismiss you? Okay, I'll be sending out a Blackboard announcement tomorrow with a reminder about our exam, as well as the procedure for coming onto campus and details of exam 2. All right. Let me know if you have any questions in the meantime. I've got office hours today and tomorrow, so you're welcome to pop on in, or if you want to shoot me an email, you're more than welcome to. All right. So I look forward to seeing you guys again, though. I'm very excited to see you guys on Wednesday. So keep in mind that our exam is on campus, Liberal Arts Building this time, room 200. That information is on Blackboard in case you forget. And we will be starting the exam at 9 a.m. sharp on Wednesday. Okay, so I'll see you guys then. Have a good one, folks. You too. Have a good one.